Let's dive into the Bernoulli naive Bayes classifier, a specialized version of naive Bayes designed for scenarios where features are binary. Picture this. You're analyzing whether an email is spam or not. Instead of focusing on how many times a word like offer or free appears, Bernoulli naive Bayes simplifies the task, asking a straightforward yes or no question for each feature. Does the word free exist in this email? Yes or no. Does it have an attachment? Yes or no. This classifier works wonders when binary presence or absence is more meaningful than frequency. The Bernoulli naive Bayes classifier operates under a few key assumptions. First, each feature, whether it's the presence of a word, a tag, or another binary characteristic, is considered independent of the others given the class label. For example, it assumes that the word offer being present in an email doesn't influence whether prize is also present. This independence assumption simplifies the computations while still delivering impressive accuracy in many tasks. Now let's talk about how it handles data. Bernoulli naive Bayes utilizes a Bernoulli distribution which models outcomes that have only two possibilities: true or false, yes or no, 1 or 0. For example, in a text classification task, it determines the likelihood of an email being spam by looking at whether specific words are present, value 1, or absent, value 0. This focus on binary data is what makes the Bernoulli classifier so effective in tasks like spam detection, where the presence or absence of specific keywords can be a critical clue. What's fascinating is how well it scales to large datasets. Bernoulli naive Bayes is both simple and efficient, meaning it can handle high-dimensional data, such as text documents with thousands of unique words, without getting bogged down. That's a big reason why it's so commonly used in real-world applications, where datasets often include a massive number of features. But here's where things get interesting: the independence assumption. In reality, features are rarely truly independent. Words in an email, for instance, often appear together in meaningful ways. The phrase limited offer might carry a stronger spam signal than the words limited and offer considered separately. Bernoulli naive Bayes doesn't capture this context, which can limit its performance in some situations. Even so, Bernoulli naive Bayes is a reliable and practical tool when applied to the right kind of data. It's especially useful when your features are binary and when the simplicity of modeling independence helps you get fast and effective results. But what happens when your data isn't binary, or when you want to account for frequencies rather than mere presence? That's where the multinomial naive Bayes classifier comes in, and we're about to uncover how it opens the door to even more possibilities. Let's keep building this story. So far, we've taken a deep dive into the Gaussian and Bernoulli naive Bayes classifiers, each with their own unique strengths and ideal use cases. The Gaussian classifier thrives in the world of continuous data, relying on smooth distributions and bell curves to handle things like measurements and numerical scores. The Bernoulli classifier, on the other hand, is built for simplicity, dealing in binary yes or no questions, perfect for scenarios like spam detection, where presence or absence is all that matters. But what happens when you move into a space that's neither purely continuous nor binary? Imagine for a moment you're analyzing text data. Think about a product review where words like amazing or great might appear multiple times. In text classification tasks, it's not just the presence of a word that matters, but how frequently it shows up. A single great in a review might indicate a positive experience, but if you see great repeated 5 or 6 times, it signals enthusiasm. Frequency starts to carry real weight. This is where we encounter a new challenge. Binary approaches like Bernoulli don't account for repetition, and continuous models like Gaussian aren't built for data like this. You need something that thrives in this middle ground, a classifier that can capture and leverage the frequency of discrete data to make predictions. Enter the multinomial naive Bayes classifier. Now, let me set the scene. Think about all the real-world scenarios where frequencies dominate. Spam detection systems don't just look for the word offer, but consider how often it's repeated across emails. Sentiment analysis tools don't just check if the word love is in a review, they measure how strongly it's emphasized by repetition. Recommendation systems analyzing product descriptions or user comments rely heavily on counting patterns in data. All of this requires a classifier built to handle not just whether features exist, but how much they appear.